Welcome, everyone, and thank you for joining us for today's webinar, How to Tackle the Video Latency Problem. Before we jump into the presentation, I'd like to point out some of the features of the webinar platform that we're using today. We plan to have plenty of time for Q&A at the conclusion of the presentation, so please submit your questions by typing them in the Ask a Question box, which appears under the slides being displayed on your screen. I also want to point out there is a Resources tab located near the top right of your screen. There you'll find several resources related to today's topic. And finally, it is my pleasure to briefly introduce today's speaker, Andrew Crowe. Andrew is a lead video engineer with Limelight and brings a broad level of experience centered around video streaming technology. Prior to joining Limelight 5 years ago, he held a variety of roles focusing on internet content delivery, product development, video, telemetry, and flight simulation. He's a graduate of Morehead State University, where he currently sits on the Computer Science Advisory Board. And with that, Andrew, the floor is yours.
Thank you for that introduction. As mentioned there, before we get in, I just want to give a fun little anecdote about video latency in the past couple of years. I kind of got introduced into video technology, digital video and imaging through defense contract work. I was working on video coming in, normalizing it, and sending it along the way, and things like that. And I remember explicitly one meeting where we had some high-up government officials that got so excited when we announced to them that we were decreasing the default latency of our product from 10 minutes of video latency down to 1. And they were so excited about that. Now we're talking here on this webinar about the various latencies from traditional TV latency down to sub-second. And so in just a few short years, the internet has changed drastically in the scope of delivering video and media to viewers and consumers at record speed. So we want to help you guys figure out what's the correct solution for you, and hopefully help you know how to go about implementing that in the best way. So let's take a look at the agenda here. Pretty simple. We'll go first into some video streaming basics to lay some foundations, make sure that everybody's up to speed. Won't spend too much time there. I want to do a quick review of the products that we have at Limelight that cover the range of latency and feature completeness, and then the real technical details are going to be where we dive into the Limelight real-time streaming product, how we're using Webrtc, typical Webrtc workflows, what we're doing, and then we will be leaving some time at the end to do a quick recap and have some questions from the viewership. So getting right into it, video streaming via Rtmp. It's one of the most ubiquitous types of streaming if you think about streaming on the internet, especially in the classic sense. Back in the early days of video streaming, most things were Rtmp, especially if you're talking about live streaming. This is the Adobe real-time messaging protocol. Important to note here, it's TCP based, so you're doing a TCP connection and then you're overlaying the real-time messaging protocol on top of your TCP connection to do your audio, video, and some data streaming. And that's a two-way street. You have audio, video going one way typically, and then a bidirectional data channel. There are extensions to that. You can use it to do two-directional audio, video. With Rtmp, since it's just sitting on top of TCP, it's got that the specific messaging protocol. It's written for media delivery. So the AV data is sent as soon as it's available. You have a frame ready from your encoder. We're going to send that now. Next frame, as soon as it's ready, we're going to send it immediately. And so you get a very low latency. It is dependent on the network. And it also, as part of the punishment of that latency and the way that it's built, if you have a poor network quality, you're going to get really, really bad quality video. You're going to get a lot of fragmentation, a lot of that digital green squares and odd stuff showing up as it's not able to keep up. And with Rtmp, you're generally doing the direct connections, and you're not able to leverage CDN, which we'll talk about with the HTTP streaming section. So the typical Rtmp workflow as it initially sprang up was you'd have some sort of producer and several clients. You would stream generally directly to those clients, and this is you're looking at streaming audio stations in the mid to late 90s were very popular on the internet. But there's a problem here in that it doesn't scale well at all. So what can we do to try to increase our potential audience with Rtmp? We can put a proxy server in the middle. So now with a proxy server, we're streaming Rtmp in to that, and then it can handle many more connections than our weak little production laptop here. And then if we need to scale that even bigger, we can put in a fan-style relay system. We can stream into multiple ingest points, and then again have a fan-style relay system. So it scales better, but it's still not great. Because what about that little old iOS device down there that is on some low bandwidth connection and can't view your high quality stream? Well, it's just going to have a real bad experience because there's no provisions in Rtmp to do anything about that. So what you end up doing is sending in high, medium, and low bit rates to your Rtmp proxy server, and then it can proxy out according to the bandwidth of each connection. So you've effectively tripled the workload on your production side on this little laptop on the left, and you've greatly increased the complexity of delivering it to the viewers. So how do we take the concept of taking these multiple renditions and make it much more efficient to deliver over the internet? Well, we use HTTP. So as we know, CDNs, which are content delivery networks, cache HTTP content at the edge or various regional hops as things are delivered so that we can efficiently deliver bytes to you very, very quickly without going back to origin and causing DDoS to some origin when a site or a piece of media gets really popular. We're able to kind of do that shielding and deliver it really efficiently at scale. And when you look at video, well, with Rtmp, we were doing frame by frame by frame, each frame individually. That doesn't really lend itself to HTTP style packets. When you start talking about multiple renditions, now we're spreading that out even more. So what we've done, and I say we in the sense of the video engineering community at large, we've taken the scope of the CDN and say, how do we use that for video streaming? Well, we chunk the content. So if you're familiar with digital video, you should be familiar with the concept of a group of pictures or a GOP. That is essentially a keyframe that has all your video information or all of your image information in that until the frame just before the next keyframe. And the other frames are going to be P or B frames, generally not B when doing live video. So you'll have a keyframe and then some predictive frames that are referencing the data that's come before them. But those can't be displayed without the information from the frames before them. So we segment there from the keyframe to just before the next, and we call that a chunk or a segment. And we can now take that, wrap it into some format like a transport stream for HLS, for instance, and deliver that to the CDN. It can now take this very simple to understand file that says my stream -1080p segment number 10 .ts, and it can cache it and deliver it to a multitude of people really efficiently. So we get efficient multi-bitrate delivery, but we introduce latency. So if we're now no longer sending every frame as it's available, we have to wait for a frame before the next keyframe. That could be anywhere from 1 to 10 seconds, depending on how your encoder is set up, depending on how your live transmuxer is set up. you have a wide range, and so you're going to wait, you're going to cause latency there, and then you're going to deliver it to the CDN, and it's going to have to propagate, and then the player is going to get those, and the player is generally going to want a little bit of a buffer, right? You don't want to hit a space where your connection drops for just a few seconds and that causes your video experience to degrade severely. You want a little bit of a buffer. So now we've added even more latency to our playback. So we're doing this. We can now scale video, but we've added latency. We've moved the other part of the scale is that we've moved some of the rendition logic away from that proxy server down to the player. The player now has a manifest that lists out these different renditions and chunks, and the player can know, I downloaded that 10-second segment in a half a second. I have headroom in my bandwidth. Let me request a higher rendition. Or on the inverse, it took me 15 seconds to download that 10-second segment. I better drop down to a lower rendition so that I can display the video in real time. And so we scale a little bit better by moving some of the processing onto the edge or the viewer. So how does that work in a sense? We've got these high, medium, low, and we'll just show a quick graphic here to help visualize how the HTTP adaptive bitrate streams work. So we've got our little video chunks, we've got audio in there as well, and then we've got metadata describing that, all wrapped up into a container. The container you may think of as MP4, AVI. For this case, I would say we're looking at some HLS stream, and it's a .ts transport stream container. So we've delivered a manifest that describes all these to our player. Our player says, let me start in the middle at the initial bit rate. We have a really good connection, so our player switches up to HD. You're probably familiar seeing this when you watch VOD content online, where it starts pretty medium, and then if you've got a good connection, after 10 or so seconds, it will get better quality. That's what's happening here. This player is saying, I can do better, let's do better, let me pull these. But now somebody interrupts your connection. You've got a roommate or a son now on some BitTorrent site downloading a legal copy of Linux, but he's still interrupting your viewing session. So you go and you say, hey, stop doing that. I'm trying to watch this show. I need to do it for work. So they stop their deeds that are impacting your network, your bandwidth recovers, and your player now sees that I'm collecting those chunks quickly. Let's increase the bandwidth. So again, the master manifest here is going to describe your renditions, the chunk sizes, your codecs, both video and audio, so you can have different quality, you can have different languages of audio so that you can switch easily there. You can have DRM information in there, other metadata, perhaps subtitles and that kind of extra data listed in your manifest. And then the player has all the logic on its side to do the downloading and the playback. So with the fundamentals of the video streaming on the internet kind of laid out, let's talk about what Limelight products have and how they map to the latency problem so that we can do some comparative analysis. So we've got a couple of products here titled MMD, and those are multi-device, multimedia delivery. So we've got MMD OD, which is on demand, or sometimes referred to as video on demand, VOD. That is doing just-in-time packaging of the video on demand content. And that is essentially taking a single source of your content, maybe it's multiple renditions like 1080p, 720p, and then a standard def, and it's making it available for all the different devices, whether that's Microsoft Smooth Streaming for some legacy Windows device, or it's HLS for some Apple iOS device, or it's MPEG-Dash for any number of devices. With MMD Live, we're taking the same concept, but we're doing, rather than VOD content that's stored on some disk, we're doing it in real time. So we're using that Rtmp input into a specialized just-in-time packaging server that's going to then take the Rtmp, let it spool up a little bit so that we can do the chunking and deliver the adaptive bitrate HTTP out. And we'll do that again for HLS, MPEG dash, and smooth streaming as required by the viewers. We also have a product called Video Acceleration. Much simpler. It's a CDN configuration, essentially, to deliver your HTTP chunked content. We basically just pull that from an origin that you specify, efficiently deliver it over the edge to your viewers so that they get it really quickly, and your origin, your encoder and your origin are not swamped with requests from end user clients. And then we have real-time streaming. And so this is where we start to get into the very, very modern segment of low latency streaming. We are sticking with Rtmp input because we need that low latency frame by frame connection, but we're switching from Rtmp output to Webrtc output. And we will describe that in great detail later on, but that is what's allowing us to get sub-second latency for this product. So to compare latency streaming solutions, on the left there, you've got your traditional HTTP live streaming. So that's going to be your traditional HLS from Apple, and then MPEG dash and smooth streaming, where you have 10 or so second chunk sizes. You've got to wait for your encoder or your packager to bulk those up, get them ready, give them to the CDN. The CDN's then got to propagate. The player has to download. The player has to build a buffer. And so you end up with a significant amount of latency there. Comparing cable TV latency, which is a lot of users' target realm, is just matching cable TV. We have MMD Live small chunk. So if you reduce your chunk size down from 10 seconds to 2 seconds, you're going to greatly reduce your latency. And you're going to be able to deliver it much, much quicker over the edge. We've got Limelight Video Acceleration, where we can take even smaller chunks from your origin and deliver them rapidly over the CDN. Low latency CMAF is an emerging technology that aims to reduce the latency at the new end of the specs HLS and dash, where rather than doing the full chunk, we're keeping that chunk mentality, still delivering it over HTTP, but we're doing essentially micro segments inside of each segment that we're making available as soon as we can. So not quite Rtmp level frame by frame, but somewhere between that and the HTTP live streaming full chunks methodology. And then all the way on the right there, just under the 1 second barrier, you've got Limelight real-time streaming. I want to note here, and you'll see as we get into it, that as you go further to the right, there's kind of an implied or an intrinsic need to have more technical resources. Doing traditional live streaming, it's been around for a while, so there's a lot of resources out there for playback, for creation of the content, etc. For doing this real-time streaming, you're getting down into the nitty-gritty with some low-level protocols, and you need somebody that knows their stuff in order to implement it on both ends to make sure that you are staying as real-time as possible. So before we get into real-time, let's again go back a little bit to the start of the latency paradigm with MMD Live, where we're taking in Rtmp to our MMD Live servers. We're doing just-in-time packaging here. So we have the option of doing single or multiple bit rates of Rtmp input. If you're doing multiple bit rates, then all we have to do is transmux it into the different formats and deliver it out. If you're doing a single bit rate, we can stick with just transmuxing and delivering that single bit rate out, or we can add a transcode step here as well, where we take your single high quality 1080p rendition and we provide it as well as several lower quality renditions so that all devices can play it back. So all of that's customizable. You can set your own output bit rates. It's a really efficient product that we've been working on for a long time and have many, many satisfied users. It's very, very simple to use. There's no infrastructure on the producer side. We're doing the full transcode transmux step. We're delivering it all to the clients. All you have to do is send in an Rtmp video stream. On the CDN side, we're able to leverage, because again, this is HTTP streaming on the CDN, we're able to leverage things like the Limelight Media Vault, token-based access control. We can do geo-blocking, and all of the things that you would expect a quality CDN to be able to do. Now, video acceleration is very similar, except that rather than sending in an Rtmp input to a specialized server that's going to do all the heavy lifting for you, as the producer takes on some of that lifting and does the encoding and the chunking to multi-bit rate on their own, uploads to some origin storage, and then the CDN pulls content from that origin storage as soon as it's available to deliver it. So this may be more versatile for some customers, but it does require a little bit more technical know-how, as you have to set up the encoder, you have to set up the origin, and efficiently connect all that stuff up to the CDN. You are still able to use all those fun CDN products like the Media Vault and geo-blocking and everything that you would want because it's being delivered HTTP. Now here we get into this transition of WebRTC. And it's a different slide. We're not going with the pretty graphic just yet. And I wanted to make that point that it's a little bit more technical. So we're shifting away from graphics and getting into text. So WebRTC allows us to do this ultra low latency sub-second delivery. WebRTC is the Web Real-Time Communications Protocol, and it's defining a real-time communication standard of data and media between browsers. That's how it started out, was intended to be browser-to-browser communications. What's really fun about WebRTC is that it still is in active development. So as we're working through this, as you're working through this, if you find some sort of detriment or some area where the specification may be able to be improved, you are encouraged to submit questions or suggestions or fixes to the working group that may be rolled into the standard. So this framework, as it's still in development, it is still pretty well defined. You've got APIs for browsers because of this, things like media stream, RTC peer connection, RTC data channel connection, etc. I want to note it is open source. Google open sources their implementation, I think, in 2011 initially, and it's been in active development since then. And in the past couple of years, it has gained a lot of traction and sped up. So because it's open source, there's a lot of active projects. I think last I was able to get some numbers, there were over 1,400 active open source projects using WebRTC. You've got a lot of, out of those, some boilerplates and projects that you can start off from or use as reference. So it's really nice to be able to work with. A little technical, but still very, very easy to get into because of the hard work of people in the last 8 to 9 years. So I mentioned 1,400 or so projects that are using WebRTC. Let's talk about numbers and how big this platform, this protocol really is. So in 2018, Google was talking about WebRTC at a conference, and they mentioned these numbers: 1.8 billion weekly minutes of audio or video in Chrome. So that's just Chrome, their browser. They're not tracking usage in Safari or Firefox or Internet Explorer or Edge or whatever Microsoft has nowadays. That's just in Chrome. So I like to say, break it all the way down, that's 180,000 minutes per minute of audio video data delivered over Chrome with WebRTC. And that was in 2018. And I would venture a guess it's significantly higher than that for 2019. Facebook, it uses WebRTC kinda for Messenger and Live. WhatsApp is kind of using a weird mishmash of it. And then I think we've also got new things coming out. Discord and Slack are kind of using it again. One of the new applications that's starting to get traction with the youth is House Party, using WebRTC for doing video sharing amongst groups of friends. So there's a lot of products out there, ranging from the very, very tippy top of the big boys of the industry, all the way down to kind of evening projects from open source communities. And so Naturally, Google was one of the first people to get in on WebRTC. They worked on their open source implementation. They're going to be one of the big supporters of it in their browser. So in this support for WebRTC graphic, you notice Chrome is way over there on the left with all of the support things checked off. On the right, you'll see Safari, and the reasons for that are really down to the mandatory codecs. WebRTC spec defines that you must support VP8 and H.264 encoding video. And so Safari does not have, at this time, VP8 support, which is why it's got that not green color. So they are working on that, is my understanding. But there are also a bunch of other bugs reported in the Safari implementation of the WebRTC protocol. So if you're able to avoid Safari, for now, that's probably your best bet. Push people towards Chrome or Firefox or some browser that has more complete support. So what is it that makes WebRTC real-time? You got part of the name, Web Real-Time Communication. It's in the name, but can we just trust it, or do we need to know? We need to know what makes it real-time. We can't just trust the name. And what's the key difference here is UDP. So on that first slide, when we were talking about Rtmp, I called out that it's on TCP. So TCP is it has a connection, and then every packet that's sent is going to get an acknowledge to make sure that it was received appropriately. So every packet is kind of sequential in nature, and you need to make sure that you get all of them. It's really good for doing VOD. It's really good to make sure that your video is of the highest quality. You wouldn't want to have a whole 5-second chunk of video be not playable because of one missed packet. But with UDP, you're just kind of sending them and hoping they get there. You've got no acknowledgement from the receiver that it's gotten there with the UDP protocol. So that allows us to just fire and forget. So there's a lot less overhead. And with real-time video, you probably don't care if you miss one packet. You would rather stay real-time than have every single frame of video be perfect, because you can probably just discard a single frame and keep going. And most viewers would be none the wiser because they're very invested in this ultra low latency interactive product that you've built. Now, because we don't have some of the advantages of TCP, we do have to implement something. And so WebRTC gives you the ability to do some flow control and congestion control and error checking that's not necessarily as part of the UDP spec. So some of that builds into things like the receiver estimated maximum bandwidth, which allows your player to estimate what it's capable of doing. So the player is not going to tell the server that I need a different rendition. It's going to be a cooperative effort. The server is going to be the one that decides eventually that the player is not able to handle this and can direct it to switch to a new rendition. Noting here, WebRTC is implementing on top of UDP. We got DTLS for encrypting your audio video data, SRTP and SRTCP for actually delivering the media and application content, and then SCTP for arbitrary data channels or transfer. And so we'll get into each one of those individually. So DTLS is the datagram transport layer security. So it makes TLS compatible with the UDP protocol. And what it does is essentially, after an initial connection with UDP, it establishes a handshake, creates a tunnel so that you can reliably deliver this key exchange, essentially, and ensure that your records are not fragmented across multiple packets and that your integrity checks don't go. So what this does is we can now encrypt our UDP packets. We can do that one at a time, or we can do it as a bulk. Our implementation is using a block cipher as opposed to a stream cipher. So a block cipher allows you to just kind of do it in whatever order individually, whereas a stream cipher requires a extended in-order delivery. And then we're using self-signed cert so that we don't have any kind of delay with a certificate chain. So the secure real-time transport protocol and then the secure Rtp control protocol, which is the secure real-time transport protocol control protocol, allow you to do encrypted payloads of your audio and video data. So we've done that DTLS connection, we've done a key exchange, we've gotten that information. Now we're using that key that we've received from DTLS to encrypt our media. So one important thing to note here is that while we're encrypting the UDP packets, we are not encrypting those headers. So any kind of extra metadata that you're putting into UDP header is going to be exposed. Your IP will be exposed. So it's not a full protection scheme, but it does allow you to prevent undesired people from intercepting and receiving the video without your permission, without you being part of that DTLS key exchange. So the SRTCP is responsible for actually delivering those packets. So it does establish an out-of-band control channel for each stream so that you can send extra data. That's where we get into the receiver estimated maximum bit rate. That's trying to allow the player to know how quickly it can pull down packets. You want to know if you've dropped a packet that may cause a single video frame to not be delivered, and you need to make adjustments on the player side for that so that you don't just play the next frame as soon as possible. You may need to put a slight delay in to normalize that against audio, or just to make it a more pleasurable viewing experience. So there's a wide variety of things that you can do with SRTCP to out of the bands of the normal audio video delivery, make sure that it's going well and that the experience is as high as quality as possible. So I mentioned earlier the stream control transport protocol, and so this is what allows us to have an extra data channel. And so it's actually an arbitrary data channel. So this is important for any number of things. Because it's not specified what this thing can do, you can do a lot of things with it. So in the use case of Google Hangouts or Facebook Messenger, you're going to be using Webrtc to do the audio video connection so that you can do that web conference. And so let's use the example of Hangouts. You're opened up in your work Gmail window and you've got to send a message over to your colleague and you're trying to work through some document. You say, you know what, let's just get on a screen share and go over this. It'll be quicker. So you pull it up in a screen share and you make a little bit of progress, but your colleague says, you know what, it would be a lot easier if you just sent the document to me and I can pull it up and follow along here. I'm having trouble seeing all the text and data that you're showing on your screen. Can you send it? And you want to make sure that that is sent securely and efficiently, but you don't want it to interrupt your audio-video connection, so you can use the stream control transmission protocol to just arbitrarily send that document over. It's not necessarily the best usage of it. It's just an example. You would also want to note that the chat on Hangouts is probably going over, in this instance, SCTP, or it could at least. I think it's still running over XMPP, and so they're kind of bonding that. But if they wanted to sync up chat or other data with the audio-video experience, they could. The other neat thing about SCTP is it's kind of in between TCP and UDP in terms of configuration of what it does. And so this little table here I pulled from bloggeek.me, a really good resource for Webrtc technical information. So SCTP, where TCP is making sure every packet has an acknowledgement, reply, hey, I did get this one. UDP is doing none of that. SCTP can be configurable. so you have configurable reliability. Do you want it to be every packet? Make sure it acknowledges. For really sensitive data, maybe. Some other data, you may say, you know what, retry 3 times, and if it still didn't work, give up. Something's wrong with that. We'll just move on. So it's pretty neat in that it's configurable, and it is, again, it's tunneled through DTLS, so you're getting some of that confidentiality. So what is it that makes Limelight's real-time streaming unique? To be straightforward, it's the fact that we are at a core CDN business. Content distribution is our game. So we have easy integration with our CDN. We're leveraging integration with our DNS product. We have core ingest locations, relay and edge server locations all across the world so that we're able to ingest Rtmp as close to the producer as possible, and then relay it over our CDN backbone to the edge to the viewer, as close as possible to the viewer. Keeping with the traditions of all of our live streaming products, we have redundancy at all points to make sure that our product is stable and that your content is delivered effectively. And again, we're leveraging our existing live streaming expertise. MMD Live and video accelerations are established, well-supported products, and so we used teams that worked on those to make sure that we were implementing real-time streaming as effectively as possible. So we're using our dedicated hardware network backbone. We're using dedicated development, operations, and support teams. We have dedicated SDKs and APIs, UIs, reporting tools, documentation, etc., aimed at customer integration. I bring all this up to kind of loop back to the point that I made on that nice graph with a downward trend from normal latency down to ultra-low latency. As you get to the ultra-low latency, sub-second latency spectrum, you need more technical resources in general. So to deliver this to you, we've allocated a significant number of technical resources. To implement it properly, you will want to have at least some technical resources. It's not going to be as plug and play as some of the lower or standard latency products. We've made it easier, but there's still some work to do. So on the left, a typical WebRTC workflow is described here. This is what I was saying, with a Hangouts like kind of conferencing where you're working with multiple people. You have multiple cameras on. Everybody can see everybody else. You've got multiple peer-to-peer connections. This was how WebRTC was really initially intended to work, as kind of a browser-to-browser video sharing. And then on the right is granted, it's very simplified, but it is an implementation kind of overview of how we do it. You take your multi-bitrate encoder, Rtmp into our ingest, and then we can relay that out to the edges via the CDN and deliver it to a larger number of viewers. So rather than doing several to several, we're doing one to many, which is fairly unique to the WebRTC spec. So now that we've covered a lot of the technical details of WebRTC, I wanted to go back to this nicer graphic that we get from our product team to describe how we're doing it. So you can see the redundant primary and backup ingests and relaying out to the edges that are then doing WebRTC to the clients. One thing I think I may have skipped in a previous slide, and I'll cover now, is the ability to do multi-bitrate with the Limelight real-time streaming. It's not part of the WebRTC spec. It really only allows for one video rendition and one audio rendition. We've added some of our video expertise in development to build out a solution that allows you to stream in multiple bit rates per what we call a slot. You may think of it as a channel or a stream. You can send in your high quality, middle quality, and low quality, and we will build out an adaptive bitrate ladder so that when we're delivering that using our SDKs, the player can see what it can do and then the player and the server can work together to figure out which one of those bit rates, which one of those renditions is going to be the best experience. Because again, you want it real time. You're probably more invested in getting the video packets as soon as possible than you are having the most HD quality. You want it now. You don't want it in 3 seconds at a higher quality. So we have extended WebRTC with real-time streaming to allow that solution, which is pretty neat. I wanted to make sure that I got that point out there. So speaking of the support, what we have available, we've got APIs for provisioning. So it's RESTful slot management. Again, I describe slot as kind of a stream or a channel that is available to you 24/7 to stream to and broadcast over WebRTC to any number of viewers. We have integrated player or viewer that's using the standard WebRTC APIs. That's available via HTML or SDK, or HTML or mobile SDKs, mobile both iOS and Android. And then we've got this nice UI, part of our consolidated provisioning UI called Limelight Control. And then we've got viewer metrics and reporting, and I've got a little clip here essentially showing, you can look at viewer hours, you can look at who's viewing, from how many people are viewing from where. This is test content, so what you're seeing here would be our developers in the States and then some of our engineering resources in Lviv, just a quick test of our UI. And so to wrap up, Limelight has a variety of live streaming products that range from your traditional live high latency down to roughly cable TV latency, and now industry setting or raising the bar across the industry with real-time streaming sub-second latency to get you even faster than cable. And I think that brings us to the end, and we've gotten through this in a good amount of time, which has allowed for some questions, and I see some have come through. So my presentation coordinator here, I think, can hopefully read some of these questions out for me, and I'll do my best to answer.
Sure, Andrew, I can help you with that. First question, is any proprietary hardware required on your network to allow real-time streaming? And does it support two-way video streaming?
Okay, so two-part question. We do not have any special hardware. We've got some special software, but really we're not doing any transcoding or anything like that. So we're just efficiently transiting the Rtmp, and then we're doing a software-based transition at the edge from Rtmp to WebRTC to deliver it down. As for two-way video, you can, not in the traditional sense of the way that the browsers work, but you can set up a kind of a dual slot, two-slot solution, and then use our SDKs to join those together if you wanted to have some sort of kind of conferencing solution. The presentation coordinator here is also part of product, so he may be able to answer the two-way video if that wasn't explicitly correct.
No, I think you got that one very good.
Okay.
Great. The next question is, how does Flash and its upcoming sunset fit into or affect this discussion? I know that we have certainly talked to a lot of customers that have been using Flash streaming for a long time and trying to figure out, where do we go next from where we've been?
Yeah, absolutely. So I'll jump back to this. So on this realm, Flash Live video is probably at about somewhere between low latency CMAF and real-time streaming. So Limelight is, I believe we're going to be supporting Flash Live video through the end of 2020, and then we will probably look to sunset that product as well. We have with our MMD Live solution, we do allow you to do Rtmp out. So it is effectively a very, very similar solution using our MMD Live. I'm not sure about the latency numbers on that. If you don't require a massive, massive audience, which typically with Rtmp or Flash Live, you're not looking for mass broadcast level. Real-time streaming is a very, very good option to transition away from Flash. Now, once the low latency CMAF products are a little bit more well refined, maybe in a year or two, those will be fairly well standardized. Those are going to be a really good option for doing low latency at large scale with support from the CDN.
Great, thanks. Just remind folks, if you have any questions, go down to the Ask a Question and type in your question. A few more here. Next question, is Webrtc really scalable for large events? I thought there were limits to the scalability of the protocol.
So this kind of loops back to that first question where they asked about hardware. We can scale as big as we want, as if we have as much hardware as we want. So what we're doing is leveraging our CDN that we have hardware in points of presence throughout the world. We're using a nice set of potentially relays to go from your ingest point, relay out from there, and fan out to multiple edges. And Webrtc scales about as well as Rtmp or Flash Live because it's doing a very similar thing. So it may be a little bit more overhead in maintaining connections because it's a little bit lower latency, but it does scale fairly well. And our first attempt at this, we are really the first people to be approaching this from this perspective of scaling it one to many, because it was designed as you said, as a peer-to-peer type solution. We've learned some lessons, and we're looking to improve on what we're already doing at scale. We're looking to drastically improve that in the coming some amount of time. I'm not exactly sure what our roadmap says, but it scales medium well for right now, and in the future it will scale really well, speaking for Limelight real-time streaming anyway.
So next question here, what is the lowest latency that is possible when using traditional HLS or dash streaming? I know there's a lot of folks trying to figure out how low can I take HLS or dash? What options might be available for them?
Right. So, with traditional HLS and dash, not low latency CMAF, that's going to be where you are building up a number of frames in order to get a group of pictures, put those into some container, and then deliver those out. And then once the chunk is available, now you have to also do a manifest update to notify that there's a chunk available. And the player has to pull down that manifest update, look at it, say, yep, there's another chunk available, let me get that. So if you go as pretty much the lowest that you're going to want to go with traditional adaptive bitrate HTTP streaming is going to be 1 second chunks. So you've got 1 second right at the beginning with your encoder and your packager. Then you've got a little bit of delay while you propagate the chunks and the manifest. Your player is probably not requesting manifests at a 1 millisecond cycle. It's probably doing it every half second or so, depending on the chunk size. So you've added in another chunk of latency there. Now you've got to download it. So we're at least at 2 seconds, and the player is probably going to want a little bit of a buffer before it starts playing so that it can give you a good view and quality. So you're really looking at 3 to 4 seconds is the most reliable or the lowest that you would want to say that you could reliably do with small chunk traditional live streaming.
Great. And I think that's the end of the questions that we have at this point. Diana, we'll turn it back over to you.
Okay, well, great. Well, thank you, everyone, for joining us today, and thank you, Andrew.
Thank you.